Hello, I'm Richard, one of the maintainers of LocalAI, and in this video I'm going to give you an introduction to the LocalAI platform and cover the basics like how to install it with Docker, how to install and configure uh, AI models and the backends that run those models. And I'm going to cover things you can do with the models, such as chat. So you can chat with large language models and get them to produce code, which you can view within the user interface. And you can chat with vision language models, which allow you to um, give pictures to the AI and have the AI analyze the pictures. And we're going to cover other modalities like image generation. We're not going to cover video, but if you have a big enough GPU, once you've seen these other features, you'll be able to figure out video. It's just like image generation. And we're going to cover text to speech.
The quick brown fox jumped over the lazy dog.
And music generation. And we can bring all these other modalities together into a voice assistant. Hello, can you tell us what you can do?
Sure, I can help you with all sorts of things. I can answer questions, tell jokes, help you
Okay,
write
that's
stories or
enough.
emails,
Thank you.
and even
And in the process of doing all these things, we'll learn about how to debug um, problems and view the requests you've made to models. These kinds of things that are sort of incidental to actually using um, these features within the user interface. And at the very end, we'll go into the application programming interface, the API of LocalAI, which allows you to do a lot more than what's exposed in the user interface. Um, and there are some features that we're not going to cover, such as agents and these experimental tools and user accounts. And there's a lot more going on in LocalAI that's just too much for this first video. So let's give some history first about LocalAI. It was originally created by Mudler, otherwise known as Ettore, who created it in 2023. And originally it was a wrapper around Yama C++ and some other backend inference engines. And since then, it has evolved into something that is not just, it used to just provide like an open AI compatible API. And of course, things like Yama C++ now have that built in. But local AI continued to evolve, and it's now like a complete AI platform. And it supports multiple APIs, like it also supports Anthropic's API, it supports the OpenAI Realtime API, which I added, and it supports open responses, and it also has, it's become very modular in that you can install different inference backends, so alternatives to Yama like VLLM, and sort of models release their own transformers based implementations. It supports a lot of those for different models, and also it supports models that um, are quite different to large language models. So it supports things like object detection through the API, and it has its own APIs for those sorts of things. And historically, it often got compared a lot to Oyama because originally they both started out as wrappers, but they long since diverged. And often there's a lot of criticism of local AI saying it's more complicated or it's harder to get set up than OYAMA. Recently that has changed because we've put more focus onto user experience and bug hunting, but also local AI is just a completely different thing, and it's trying to do a lot of different things, and it's on a different trajectory to OYAMA. It's not really comparable. Okay, so an interesting fact about local AI is that it actually develops its own source code to an extent. Okay, so the type of model we can run on our single H200 that was donated to us, it's good, but it's not quite as good as Claude. But it's enough that we can develop local AI using local AI's own agents. And Ettore wrote a blog post on this. We're using Minimax with a very, very heavy quantization. And we also use Qwen 3.5 now as well, one of the bigger Qwen 3.5 models. And we use this with local AGI to basically we have a team of agents that hand out work based on tickets that Ettore assigns or the agent searches for and assigns to itself. And then we have a coding agent that goes in and produces pull requests. And you can see these on local AI's GitHub. The local AI bot, does a lot of stuff. It's all quite routine stuff. Sometimes it does like more complicated code changes, but you can see that it's one of the top contributors. It actually comes before me, which is a bit embarrassing. But yeah, it does a lot of routine stuff that genuinely takes away work from Ettore or me. So it's just one of those interesting things. Okay. So for installation, I'm going to do it with Docker Compose. This is a slightly more complicated way of doing it. In fact, the simplest way to install local AI is just to point Claude Code at its website and say go install it, and it will do it. But obviously, if you want to run local AI, maybe you don't want to use Claude Code, or maybe you want to understand how to do it yourself properly. So I'm going to go through it in detail, and we're going to write a Docker Compose file so you know what's going on and it's not just magic that coding agents produce. So I have a repository which shows some Docker Compose templates, and in a moment I'm going to go through and write one with you manually. So okay, so installation. So the simplest way to install local AI is to ask a coding agent to do it and then just accept whatever it does. But we're not going to do that. Instead, we're going to go and look at how to create a Docker Compose file and how to install it using Docker. We're going to do this because, first of all, it works across, I'm on Linux, but it also works on Mac OSX, and it works on Windows with Docker Desktop. So we're going to look at creating a Docker Compose file, which also allows you to set up other services that local AI may need in the future, and also allows you to put some configuration in the file, which allows you to configure Docker itself all in one place. So there are simpler ways to install local AI. This is like the belt and braces way that works across all platforms, and you can substitute this section for another installation method. It's entirely up to you. Okay, so I have a GitHub repository which you can use if you want. You can use this as a template, or you can just sort of copy what I'm doing here. So I'm going to create a new file, Docker Compose local, and okay, so Docker Compose separates everything into services, and we're going to create two services. One is LocalAI itself, and another is a service for a program called Caddy, which we'll need for the real-time chat, the WebRTC chat. So we'll come back to that, but first of all, let's create the services node and local AI service, and we need to choose a Docker container image. Okay, so we can find out which image we need by looking, which page do we need to look at? Run with container. Okay, so on LocalAI's website, there's a page which shows you which containers you need for which GPU. So basically, as an NVIDIA user, we have a choice of CUDA. We have two CUDAs. We have CUDA 12 and 13, and we have Vulkan images. So we can use CUDA or Vulkan. Vulkan has the advantage that the runtime is much smaller. CUDA's just still better supported, and you may get there's some performance differences between CUDA and Vulkan as well. If you're not sure what to use, then just go with CUDA for now, because a lot of backends won't work that well with Vulkan. But if you just want to use Llama C++, then maybe you can use Vulkan. But I'm just going to go with CUDA. I'm going to go with the newest CUDA. I've not had any problems using CUDA 13, so I'm just going to pick CUDA 13. Okay. So we're going to use Quay IO's image. Oh my God. Okay. So that's the image we're going to go with for now. So then we're going to set the user account we want to run the container as. By default, Docker runs as root, and it runs the containers as root. We don't want it running as the root user. We either want to run it as our user, which by default on Linux, user 1000 is like your first normal user, which is what I've put there. So the first number is my user 1000, and 100 is the user group that I belong to. And this will vary between Linux distros. But actually, it doesn't really matter what users you put here, as long as it's not root. You can also create a new user and group just for LocalAI. It'll just affect how you can access the files if you want to access LocalAI's files outside of the container. And to find these numbers, you can just, it varies a little bit from Linux distro to Linux distro. You can just look up how to get to your user number. Okay, so I'm going to set the user so that we're not running as root. And command, which we're not actually going to use any command line options for LocalAI, but if you want to set command line options, you put it in here. And then ports. So we want to expose LocalAI to the outside world. Docker Compose, and in fact just normal Docker, create a virtual network that the containers run in, and you need to set up port forwarding from the virtual network where the containers run to your host machine in the outside world. So we're going to take, what I'm going to do is I'm going to map port 8081 to port 8080. So port 8080 is what LocalAI listens on by default. The REST API and the web interface both listen on port 8080, and we're going to map that to port 8081 on the host. So you'll be able to connect to LocalAI on 8081 either through localhost or through the IP address attached to that machine. Okay, next we have environment, where we can set environment variables. So with LocalAI, any configuration setting you can set at runtime, you can also set as environment variables. And so you have a choice of, you can either put configuration here inside the Docker Compose file, or you can put that configuration actually inside LocalAI itself. I find it useful to set things like debug here, because when you start up LocalAI for the first time, if there are any problems, you won't be able to set debug if you can't get to the settings page where you can enable debug. So you can set it here in the environment, and if later on you want to disable it because it produces a lot of noise in the log, then you can do this, and then that will disable it in the environment variable. The environment variables take precedence over the configuration file, so it's important to realize that if you set something in the environment variable, it's going to override the configuration, and so on. Okay, and then next one is volumes. So LocalAI stores a lot of data. The model files that it stores are several gigabytes, and the backends as well are very large. They include a lot of software libraries for doing AI inference. And so we want to persist the data that's written to these places. Like usually a container, when you write data inside a container, it goes to like an ephemeral store, which is lost when you restart the container or delete the container. And in fact, for hardened containers, you can't even write files to the container's root file system. It doesn't allow it to prevent for security reasons. So if you want to have writable volumes, writable files, you have to mount volumes. We've got a folder called volumes, which is on the host outside the container. And first of all, we're going to add models, which is where AI models are written to. So on the left, we have our host path, and on the right, we have the path that's used within the container, which is a standard path. So we just put models here. And then backends. So backends are the software modules that actually run the models. LocalAI's core doesn't run any models. It just, it's just like an orchestration engine and platform that implements the UI and the API. The things that actually do the heavy lifting to run the AI are the backends. So the backends are sort of isolated software modules that we install at runtime, or you can install through the command line at startup. And they are, some of them are just as big as the smaller models, like in terms of the amount of software that gets installed. And we also use backends for some other types of software, such as the Opus codec, which is used in real time. Okay, and then next we've got content. So the content volume is where we write generated content. So whenever you generate an image or some music or whatever, it'll get written to the content volume. And you can see that it's mounted to temp inside the container. So usually it actually gets deleted, but if you mount it to a volume, then all of the content you generate will be persisted to the volume. And it's up to you whether or not you want to delete it between container restarts. Volumes, and then finally we have, okay, so we have data, which this basically there's some more advanced features of LocalAI which use SQL database and vector stores and stuff, and other types of database and collections. And so when you do something like enable the user accounts and authorization, then it'll use a database that it will store inside data to store the user accounts. We're not going to go into that in this video, but just to be aware that that volume is there. And then volumes, configuration. So this is simply where the configuration files go for OpenAI's settings. So when you change a setting inside the UI, it'll get written to a JSON file which will be stored in the configuration, and you can edit that JSON file yourself as well as doing it inside the UI. And you can actually use the API to update the configuration as well. So because we've mounted those volumes, we'll be able to persist that data and also look at that data as well. And that data will be written as this user and group. Okay, and something to be aware of is that when you create, if you simply allow Docker, if you don't pre-create these directories, the directories in volumes, if you don't create those in advance, Docker will create them as the root user. And then your container won't actually be able to write to these directories because Docker just creates them as root, even though you've just told Docker what user you want to run the container as. Docker will create these directories as root, and your container won't be able to write to them, so you get an error saying like permissions error or something, some confusing error that LocalAI will start up with. You need to pre-create these directories, and so the in my template I've created these directories in advance. You need to create these directories as the user you specified here. Okay, deploy. So we're using, I'm on a machine presently that has a NVIDIA GPU. And so for NVIDIA, and this is different for every GPU vendor, but for NVIDIA, we need to add the GPU to the container, or give the container GPU access. And this is how we do it. Well, this is one of the ways we do it, I should say. So we write out this magic text just here that is different for NVIDIA to every other GPU vendor. And this gives the container access to all of the GPUs made by NVIDIA on the system, which it happens to be just one GPU, so it'll get one GPU. For Intel and I believe for AMD, we do something slightly different. And actually, even for, depending exactly what software you have installed in your system for NVIDIA, it can be slightly different from NVIDIA. You just need to go and look up what is needed for your GPU. What magic text we have to write in for your GPU. And typically, if you get it wrong, you'll get a ultra confusing error message from the Docker runtime, saying something about CDI or, some other rubbish. Or in Intel's case, you just don't get the GPU and this sort of thing. So that's just something that you have to look at for each GPU. We've got documentation on the website to help with that, but it ages like milk, frankly. So at this point, what can we do? This happens to work for my GPU right now. Okay, and then we're going to add another service. So we've got LocalAI service. Now we're going to add Caddy, which is a proxy server. And we're going to add this because the WebRTC real-time chat requires HTTPS. I don't know why. This is one of the ridiculous things that happens with web technology, but even if you're running on a fully encrypted VPN, you have to use HTTPS to have a real-time conversation for security. So what we do is we set up a reverse proxy that encrypts the connection. Possibly you can do this directly through LocalAI instead by setting up a TLS certificate or something, but the easiest way is just to use Caddy because, yeah, it's what it's made for, is to do this type of thing. And what we're going to do is we're going to map a port of 8443. And for Caddy, we also need a Caddy file, which we'll go and look up in a minute. So yeah, I'll use Caddy file local, and we're gonna mount this into the container into Caddy's standard Caddy file configuration location. And for this container, we do have a command. We have Caddy run, which is going to run with this container, with this configuration file. And we have to tell Caddy that it's using Caddy files. Okay, so yeah, so this second service, I better go and look at the Caddy file. Okay, so yeah, so this second service, it's proxying the LocalAI service with TLS to these external addresses. So Leadbox is the name of the machine that I'm on, and it's saying to listen on those Leadbox and Leadbox LAN, and it's saying to listen on those domain names and provide TLS so that I can be safe on my isolated network. Okay, So now what we can do is, so I already have LocalAI running, which I was showing earlier. So we can see that this is the same directory that we were in. Now, actually, I'm not going to run the Docker Compose file we just wrote. Instead, what I'm going to do is I'm going to run this development Docker Compose file, which is what I use for developing LocalAI itself. And of course, what I'm about to show you is a development branch of LocalAI, because things move so fast with LocalAI, I might as well just show you an unreleased version, and by the time you actually watch this video, you'll probably, the unreleased version will already be out of date. So yeah, this video is going to age like milk. But yeah, so you can see the difference with this Docker Compose file is the image I'm using is local-AI, which this container is one that I built locally. So when I'm developing LocalAI, I build it inside a container and then use that container in my Docker Compose file. And building LocalAI is a little complicated, but basically all you really need to do is figure out like what environment variables you need to set on make, and then just do make docker, and it will build a development version of LocalAI from the source, which again is how I do development for LocalAI. And you can see here that I've got Docker make flags, which just tells it to use all of my CPU cores when compiling. And I set the CUDA major version to 13 so that we have CUDA included in LocalAI's core image, which isn't actually necessary. You can actually just build LocalAI's core image without CUDA or anything else, and then the backends will bring it in. But I put it straight in core because it speeds things up a bit when running. And yeah, build type, again, QBlast just means CUDA. I'm going to use NVIDIA's CUDA. And go tags auth, I'm telling it to build with user accounts and authentication, which is an optional feature, which I'm not going to show today because it's too advanced, but it's just something you can do. And then we just call make docker, which is going to build everything inside a container. And just as a little aside, I do all of this on NixOS, where like LocalAI doesn't really build properly outside of a container, so doing everything inside containers helps a lot. And you can do this on, I guess you can also do this on Windows if you can get GNU Make to run in Mac. So you sort of have this completely contained build environment here that you can do on any platform. If you want to build LocalAI from source, which you might want to do if you make some small changes to it or want to begin developing it. Okay, so that's what I'm going to run. So the way that we run this is that we use docker compose command, and we specify the docker compose file we want to use. If you don't specify a file, then docker compose will just use dockercompose.yaml as a default name, but we have, I have multiple files, so I'm going to specify the file, and then we just say up LocalAI, which is the service we're going to run. Now, something I need to show you is that, in fact, so I'm already running Caddy. So something you can do with Docker Compose, right? if I do docker compose down now, this is going to shut down any services we have running. Okay, so it's removed Caddy and LocalAI. It stopped Caddy as well because that was running, and it's removed the network when we do docker compose down. And if we want to start everything up, then we can just do docker compose up, and this will start everything. But what I'm actually going to do first is I'm just going to start docker. I'm just going to do up caddy, and then I'm going to do -d, which puts it in daemon mode. So when I start up caddy, it's going to start that in the background, and then that'll be running on the network, the virtual network that we can see it's created. And the reason I'm going to do that separately from LocalAI is because first, I don't want to see Caddy's log output. I know that it works. I'm just going to let it run in the background and ignore it. And also, I stop and start LocalAI a lot more than I stop and start Caddy. We can just leave Caddy running, and when LocalAI is not running, Caddy just won't be able to proxy anything. Okay, so now we're going to run the LocalAI service itself. It takes a little while to start up because it's scanning the models and backends it already has installed. Go to this page, refresh that. Okay, it's running. So the first thing you'll see when you start running LocalAI is that unless you specified some models and backends on the commands line, you'll start with no models or inference backends. You just get the core of LocalAI. Now, if you go to system, you can see that I already have some models and backends running here. But what we're going to do is we're first going to go and install a new model. Okay, so let's go and look at the model gallery. We're going to start with a large language model. Qwen is a good place to start. We're going to pick a small one because it'll download quite quickly. Okay, so Qwen 0.8b. So we can see from the model gallery that first of all, the backend this uses is Llama C++. So when we install this model, we also need to go and pick a Llama C++ backend. So we can start installing that. Here we go, it's installing quite quickly. If we go and look at backends, then we can type in Llama CPP. Okay, so you have a choice of which flavor of Llama C++ you want to install. What I've installed is the CUDA 13 version of Llama C++. And in fact, I have installed the development branch. And I've also got the meta package for that one. Strange. But anyway, I've installed the development branch. So as well as being able to choose what sort of GPU gubbins you need, you can also decide whether you want to go with the stable backend or you can go with the development version. And obviously the development version is basically the version taken directly from LocalAI's master branch. And I like to live dangerously, so I've got the development version installed. And you can update this whenever you want by coming in here and hitting reinstall, and that'll reinstall it directly from the development branch. Because we're on NVIDIA, we also have, as well as using CUDA, we could also use Vulkan. Vulkan works on, pretty much every GPU, and yeah, you can choose between them. Vulkan images are, the software that's needed for Vulkan is much smaller than CUDA, so the Vulkan backend is therefore smaller. The performance, I think they're actually roughly similar performance now, but that varies between backend and GPU. So for some GPUs, Vulkan will actually be slower, some will be faster. The only way you can really find out is by testing them. Okay, so let's say that we've just installed that backend, and then if we go to chat, okay, so create a new chat. And we go and look for the Quen we just installed, which is 0.8. And let's see if that works. Say hello. So, okay. Wow. That's great. Okay. It's doing a lot of thinking. So, this is something that can happen with small language models. Yeah, basically with small language models, and also with small language models where we've used quantization. So if I go back to install models and look at Quen 3.5, 0.8, okay. And if we browse to the files it's actually using, okay, we can see that we've got a small model and we're using Q4 quantization, which actually has reasonably good quality, but using a model that's less than 1 billion parameters with quantization, it's quite easy for them to get stuck in the loop. And apparently, especially in the thinking stage with Quen 3.5. So what we can do is, to avoid this thinking loop that it can get stuck in, is we can go to system, and then we can go and edit the model's config to remove reasoning, because not all models handle it well. They have it enabled, but they don't really handle it that well. So if we type in search here, now all of these configuration are documented on LocalAI's website. But you also get a little bit of documentation actually within the user interface as well. So we can add the disable configuration option and then click disabled. So we're disabling reasoning because it's enabled by default on this model, and save changes. And it takes a little while to save because it has to restart stuff. Okay, let's just check that model's, okay, let's also stop the model. So the backend that actually runs the model is like its own running process, and within LocalAI's system UI you can stop that process, which is also useful for freeing up GPU memory, which we'll see later on. Go back to chat again. Okay, so now if I try again, this time there's no reasoning and it doesn't get stuck in a reasoning loop. And there's a few reasons to disable reasoning. One is what we just saw here, and the other is, as we'll see later, is when you're doing real-time chat, you don't want it to spend loads of time reasoning. You want it to respond in under a second. And but clearly there's a trade-off, because you remove reasoning and the output gets worse for things like coding tasks. Okay, so far we've added a model from the gallery and we've changed one of its settings when there's a problem. Now you can install models from the gallery if they're there, but these gallery items come from LocalAI's own gallery, and we don't have every single model there, and we also don't have every type of quantization. So typically the models you see in the gallery will have a quantization like Q4, one of the lower ones, so you can get sort of the biggest and best model that you possibly can in the video RAM. But if we go to Hugging Face, then we can find models with different quantizations, and we just have a much bigger selection of models, and also of different types and things like this. So let's go to Hugging Face and search for a model. That's one that Omnicoder, that's it. So this is one I experimented with recently. Okay, so it's a 9 billion parameter model. I have you can see in the systems page that I have an NVIDIA GeForce RTX 5070, and I have about 16 gigabytes of VRAM. So, I mean, first of all, we can use Hugging Face's VRAM estimation, and they say that I can run everything except BF16. So I'm just gonna what I'm gonna do is I'm gonna run the highest quality one, Q80, which is usually quality that's very, very close to BF16. So pretty much the highest quality, and often you may actually prefer to run Q6 because it's almost identical quality, but it runs faster even if it fits. Okay, so let's copy this and go back to import models. So I'm going to import this model. So let's say HF Omnicoder, and then I'm going to Omnicoder 9B. I'm going to set that name myself, so it's not just the default, and I'm going to set the quantization to Q80, and we'll leave everything else as default, and then go to import model. So you don't have to set all of these fields, but if you don't want the defaults, then you'll have to specify it directly. And then import model. Let's see what happens. Okay, so it managed to import it, and now it's downloading the model. And it estimates our VRAM usage as 10.3 gigabytes, which we can actually see is slightly higher than what Hugging Face estimate. And actually, I think what we're going to find is that the VRAM by default is even higher than this. What this is actually estimating with is a small context size. And by default, Qwen 3.5, which is what I believe this is what Omnicoder is based on. believe it's based on Qwen 3.5. Qwen 3.5 actually has a context size of over 200,000 tokens. So with a context size that large, and that being the default context size built into the GUF, which is Yama C++'s file type, with that kind of context, it's actually going to use up a lot of VRAM storing the context or the key value cache. So what we're probably going to find is actually this still uses more than my GPU RAM, but we'll find out in a moment when this finishes downloading. Okay, so that seems like it's finished. Let's go back here and see if we can now use this Omnicoder 9B. Start a new chat. Enable canvas. Create a hello world. HTML landing page. Okay, so now it's trying to load the model. Okay, and we have a error message. So we've got quite a confusing error message. Basically, it's telling us that, it couldn't load the model, but the reason why is just error reading from server EOF, which means end of file. So, I mean, what it's actually telling us is that the backend, which is a separate process running a gRPC server, it was trying to read from that gRPC server's socket, and it got the end of file signal from the socket, which means that the other end unexpectedly closed, which of course doesn't really tell you anything about what happened. So what we can do to investigate this is we can click on view traces for details. And this takes us to the backend traces. And right, so the last entry we can see here is from Omnicode, and again it says it was a model load trace, it failed, and again the summary is just model load failed. But let's try and dig into it a bit further. Still not getting much more information. What we can next do is go to backend logs. And what this does is it takes us to the log from the backend inference engine and shows us the log of the inference engine. And actually, like, it's taking us to a spot in the log where we can see the problem straight away, although it's still not entirely clear. So I'll go through what we can see here. So first of all, we have some information about what Yama was being loaded with. In fact, what Yama context was being loaded with. So first of all, we can see that the context size is huge. It's over 260,000 tokens. And then we can see that we're trying to allocate a buffer of 8 gigabytes. So that's like half of the VRAM we have available. And then we have failed to allocate CUDA 0 buffer. So it tried to allocate about 8 gigabytes of RAM and it couldn't do it. Probably because it was already using some RAM for the model itself. I guess it already used about 8 gigabytes just for the model's tensors. So we were already using that RAM, and then we tried to add another 8 gigabytes and it probably pushed us slightly over 16 gigabytes because there's some other RAM that's used for things on the GPU other than the model. Okay, and then it said, failed to create context with model, blah, blah, blah. So basically what this means is there wasn't enough RAM and it failed on the context creation, which wanted to use about half the GPU's RAM when we're already using just over half for the model itself. So what can we do about this? Well, again, we can change the model's settings to override the context. So we're not going to use a context with 260,000 plus tokens. We're going to use a much smaller one. At least in my opinion, if you actually try to use Qwen 3.5 with 260,000 tokens, it's probably going to produce some nonsense anyway. There are specific tasks where you can use the full context and it'll work, like searching needle in the haystack tests and just basic search. Like, yes, long context will work. Otherwise, once you get over like 50% context, say like 100,000 tokens, you're going to start seeing like heavy model degradation. So for most use cases, we actually can't really use that full context, even if we have RAM available to do it. So let's go into edit config. We don't currently have context, so let's add search for context. Okay, we've got context size. Okay, so we've added context size. And here we go. It's predicting here. I mean, okay, so it says 0 context, but what that actually means is that it's using the default context. So it's using 260,000 tokens, and it's saying for this size context, we're going to use 18.6 gigabytes of RAM, which is kind of an approximate figure. It might be more, it might be less. So if we change this now to like one, okay, so just one token, it would use 10.1 gigabytes of VRAM. Let's set it to something reasonable like 32,000. It uses 11 gigabytes. Okay, we can fit 11 gigabytes on a 16 gigabyte GPU, no problem. And probably we don't want to use too much more than that because I don't think it'll work that well. Yeah, okay. And something just to note here is you can use sort of this graphical configuration editor, or you can edit the YAML directly, and we have some like rudimentary autocomplete and validation in here. So if we type something, yeah, you can search this and also get the same settings here. But for now, let's just ignore that and go back here. Okay, and let's try again. Let's see now whether those settings have taken. Okay, yes. And it's doing it. It's generating some code. Generating quite a lot of code. Actually, this is yeah. Okay, we can see it's used 5% of its context generating that 1,500 tokens. And it worked. It produced a landing page, which, we've got like home, we've got about. Oh, we can't click on that. That was too much. Oh no, I've lost it. Okay. You get the picture. Emacs. Wow. So it generated some code, and yeah, we can view it inside the browser. Just can't click on the links. Very good. So to review, what we did is we tried importing it from Hugging Face. We entered the quantization we wanted, which we used the highest quality. We could have gone down a bit without much loss, but I like to go with highest quality. And then we found that it actually used way more VRAM than what this suggests, and we needed to reduce the context size to get it to fit inside our VRAM. Okay, so that's chat for now. In fact, actually, sorry, no. There's one more thing that we need to point out here, which is how you can basically give images into the chat as well. So it doesn't just take text, it also takes images. So let's just use standard Quen for this, and we will try selecting a file. Now, as you may have noticed, I'm using like a weird desktop that's pretty ugly, and there's weird things that happen when on my UI. Okay, so select that file and ask it like describe what is in the image. And see what happens. Okay, we've got a model error again. And this time the allocation failure has actually managed to bubble up into the error message. So sometimes this happens, sometimes it doesn't. It just depends whether the local AI manages to pick out the error message that's significant. Yeah, it's failed to allocate memory again. So I've got another model allocation failure. However, let's go and look at the backend log. Yeah, so this time it failed just on loading tensors, which is an earlier stage of the allocation process than loading or allocating the context buffer. So the tensors are the parameters of the model. They are the model itself, like the pre-trained model. And it's not even managed to load those, but this size model should fit in our RAM quite easily. So, but we can see what's going on here. We go to system, we can see that already most of our VRAM has been used. And okay, so we're running Quen 0.8b, we can stop that, and that's going to free up the RAM. And then we can also stop omnicoder, and that's also going to free up some RAM. And moreover, we can actually, if we go into settings, so this is now the system settings where we have all kinds of features. And what we can do in here is if we want to, we can enable the memory reclaimer, which will evict backends when usage exceeds a threshold. So this works well when you have a lot of different models running on your system, and no particular one uses over 80%. But when you have like a bunch of them, say you have like 5 models running, and as soon as it gets above 80%, it'll remove the model that was least recently used, which wouldn't have helped much in our situation. But in addition to that, we also have an idle timeout, which again will remove the back end when it's idle for a certain amount of time, and this sort of thing. So you can automatically free up space. But for now, I'm just going to do it manually. I'm just going to point out that those settings are there if you want to automatically manage the system's memory. Okay, so now that we've removed those models, we should be able to load this model. Yeah, and of course it's going to take a little while to load it into. Oh, that's pretty quick. Here we go. Okay, so it's analyzed the model. The image depicts a stylized anthropomorphic penguin standing confidently. I wouldn't say it's anthropomorphic. Is it? Is it really anthropomorphic? art style reminiscent of AI generated imagery, like Mid-Journey. Well, that makes sense because it was generated by AI. Okay, so yeah, you can see that you can give it images. You can also give it images that are that contain text. So if we try and find one, take an image that contains text. And then okay, so yeah, you can give it a come on. You can give it an image, which actually this image was yeah, it's basically a picture like this, which shows my GPU usage. And you can see that it was able to read that and tell you what's in it. It was able to do OCR. Yeah, so you can use vision language models to do OCR, amongst many other things. Quen can also do things like object detection. It can tell you, it can put bounding boxes around objects and stuff like this. Although the local AI UI can't show you the bounding boxes, but it can do it. So you can ask it to produce bounding boxes in JSON. Okay. Now let's move on to the studio. Let's move on to the studio. So first up is image generation, which like a lot of things in AI, this has come on leaps and bounds over the last 2 or 3 years, and now you can do things just on an average GPU that you wouldn't have been able to do even just a couple of years ago. So one of the latest models is Flux 2 Klein, which is a smaller version of Flux 2, which is easier to run locally. And if we go to backends, importantly, Flux 2 Klein. Let's have a look. If we go in here, we can see that the backend it uses is Stable Diffusion GGML. So this is sort of similar to Llama C++, but for image generation models. And this is the one I'd recommend using with LocalAI. Another popular one is diffusers, and with diffusers you can use any model you can find on Hugging Face that also supports diffusers. So if we go to backends, diffusers, so yeah, you can install diffusers. I recommend Stable Diffusion GGML because it's written in C++ and it's lighter weight than the Python diffusers backend, but you have a choice between them, so it's up to you what you use. And if we go back to Studio, okay, so let's try generating a model. So we have a bunch of different options that we can use. Steampunk. Okay, generate. So first of all, it's going to take a little while just to load the model, and there we go. Okay, very quick. And we can generate more than one. Okay, there we go. Okay, so let's try generating 4 at once, which takes a little bit longer. But yeah, so you can see that we get like different variations, and you know, if we yeah, see maybe some slight strangeness just there in that one. And what we can also do is we can go into the advanced settings and we can change like how many steps we run the diffusion process for. So the way that diffusion works is you start with like an image of pure noise, and then it tries to reduce the noise into an actual image that you want. And if you reduce the number of steps, you get closer and closer to the noise. It already looks pretty good after 3 steps, actually. Let's try it after 1 step. Yeah, so you start off with like almost pure noise, and then the more steps you add, the higher the quality, up to some limits where basically you don't really get any return on the time investment. And yeah, in the UI, we have a limited set of options. When you're using the API, you get a lot more options you can add. Okay. Very nice. Okay. Actually seems added a little logo for us. Interesting. Okay, we can also change things like the size of the image and this sort of thing. So that's image generation. Video, as I said, we're not going to cover that or get into it just because it requires a lot of time, and I think it actually needs a bigger GPU. I'm not sure if I can get it to run on my GPU. There might be one model where I can, I'm not sure. Text to speech. Okay, so this one's quite simple and straightforward. You put in text, you get text out. Now, there's basically the main reason that this exists in the UI at all is just to test the text-to-speech models. So and otherwise there's not much reason. Some of the models
I am a
support
happy person.
some of the models support things like voice cloning and stuff like this, which we haven't added to the UI yet. We're just getting around to that. So presently you have like quite this simple interface, and usually people will use the API to create speech, where you have a few more options like the voice, and yeah, some of the models support voice cloning, like Qwen3TTS. You can set that either in the API, or if we go and look at the model configuration, then I believe audio path, yes. So if you have like a sample voice that you have of somebody, you can put that in here into the audio path, and then their the voice, the text, the speech will be generated with their voice cloned, in theory. So that's not something I've played with myself, but it is possible through the model configuration. And then finally we have, I shouldn't say finally because we still have real-time voice, we have sound generation. So with this we can generate, well presently we can just generate music. I guess you can also generate other sound effects with different models. So you can sort of ask it to generate a few, like, I don't know. Yes, it has a duration, so you can generate some music, like, I don't know. It probably helps to use real genres, but I'm just going to give it like some nonsense and see what happens. It occurs to me that maybe there's not enough VRAM again, so we'll see if this loads. It did. Okay. Okay, I mean, oh, okay, industrial jazz. Mainly just seems to be jazz, but never mind. So now if we go to the system, yeah, we can see that, okay, altogether, these aren't using a lot of VRAM at all. A-step turbo is only, well, the main model itself is only 4 billion parameters. And something to note is that it uses quite a bit more VRAM than that would suggest, because it also has an embeddings model and a VAE model, which come with the main model, which is actually this one here. And this is the case for a lot of non-large language models. In fact, large language models themselves also often have a VAE model if they're a vision language model. So they're actually like multiple pre-trained models joined together. And this means that the VRAM often will be something unexpected if you're just going by the sort of the model's main size. Yeah, we can see for this image generation model that where is it? Where are where are the files? Okay, yes. Okay, so we have yeah, we actually have a large language model being used to interpret the text before it's then sent to the actual image generation model. Yeah, I think that it takes the raw text you give it and turns that text into tensors or embeddings or something like this, which then sends to the actual image generation model to condition that model. So yeah, you actually have like multiple multiple models making this one image generation model. Okay, so next up is we have real-time talk. Okay, so the model that you use for real-time chat is special because it's actually a collection of models joined together into a pipeline. So basically, with real-time voice agents, you have a choice. You can either use a true multimodal model that accepts audio, accepts like actual speech, and then outputs actual speech or speech and text, or you can use a pipeline. Here we're using a pipeline. Now, generally speaking, AI ML researchers think that you should have like a real any-to-any model that takes voice and then outputs voice. and this sort of thing, because it's like a much cleaner thing from their point of view. You're not like taking speech and then turning it into text and then sending the text to a large language model, then taking the text out of the large language model and turning that back into speech again. But actually, when you use a pipeline model where you're doing all of these conversions, you have the freedom to swap out like your transcription model. You have the freedom to swap out the large language model, and you can change any part of the pipeline interchangeably. So there's actually kind of an advantage there, especially when you consider with text to speech. You have features like voice cloning and like features like describing how emotional the voice is and this sort of thing. And if you can swap out the text to speech model, then you can improve the voice without having to like create a completely new language model. So it stops everything being tied together because you're doing this pipeline. It's like completely interchangeable. And yeah, presently that's what we have, is we have pipelines. So in the future we will also support any to any as those models get better, but currently we're just got pipelines. Okay, so we have to choose each model in our pipeline, and we'll start with VAD because that's actually at the start of the pipeline, even though it's at the bottom. So VAD stands for voice activity detection. And basically what it does is when you send it audio data, it just chops that audio data into segments based on whether or not there is speech in it. And to run this model, you can use Celero for the VAD. And basically this model runs using the Whisper CPP backend. So it uses the transcription, the same backend we use for transcription, we also use for voice activity detection. And yeah, you can also access voice activity detection and transcription from the REST API. So you can segment arbitrary audio files. But in the real-time pipeline, we use VAD so that we can just accept data the whole time and very quickly decide whether there's actually some voice in it which needs transcribing, or whether we can just ignore this audio. And then we have the transcription model, which I'm using Whisper Large Turbo Q8. So this is quite a large transcription model, which I find copes much better with my accent than other like smaller transcription models. And yeah, it uses the Whisper CPP backend, which again is quite similar to Llama CPP. It's built with GGML. There's much more recent transcription backends like Qwen ASR and stuff, but for now I'm just sticking with this one, and this is what we're going to use for transcription to turn into text. And when it does transcribe my voice into text, it's then going to pass it to the large language model, which for this we can use Qwen 3.59b, which we previously used in the chat. We have reasoning disabled on that one, so it will respond nice and quick. It can also, if you have a smaller GPU, or if you're trying to do this on CPU, you can try using a much smaller model. 2B and 4B and everything like that will work also really well. 0.8 will even work, although you may have some trouble actually getting it to do things like calling functions and stuff like this. And then finally we have the text-to-speech model. I'm going to use Kokoro, which is a really, really small text-to-speech model. The text-to-speech model has a voice parameter, which we're just going to ignore for now. We'll just use the default one. Okay. So Kokoro, by the way, has its own backend, as do a lot of the transcription models and stuff like this. So you may have to install a backend just for the text-to-speech model you want to use. For the model name, we're going to just say GPT Realtime, because this, at least, you know, when I wrote this code, this was the default model that OpenAI used with their Realtime API. And the API that we use under the hood to do Realtime Voice is based on OpenAI's Realtime API. So it should be compatible with OpenAI's Realtime API. Okay, and then click on Create Model. Okay, so we've done that now. Let's go back to talk. Yeah, and we can see we've got our pipeline model selected there, and we can see the different components we've got in the pipeline. In session settings, we can change the instructions that we give it. So we can say something, you know, we can change from helpful voice assistant to okay. Then we can go to connect. Okay, and so when we first start talking, it's going to take a little while to load all of the models that we just specified.
Now.
Okay, can you do anything for me?
Now.
Why not?
Now.
Right, fine, okay.
Now.
And we have this fancy little diag thing.
Now. Now.
Okay, let's disconnect from there. So what you're currently seeing here is the WebRTC implementation of the Realtime, which allows you to use a web browser client. There's also a WebSocket implementation, just like how OpenAI have, which you can use to communicate over WebSockets if you don't want to use WebRTC. And so that is real-time chat. And as I said, we basically, because we have a pipeline model, we have a whole different set of backends and models that are being used. It's important to note that there's one backend that's kind of hidden from view here, which is Opus. So when you're using the WebRTC real-time client, you need to install the Opus backend, which has the Opus codec, which is used to encode audio and decode audio from the WebRTC browser implementation. And when you try to run without Opus, you'll just get an error message saying it couldn't load Opus, but you can install Opus from the backends just like any other backend. So it's nothing to do with AI. It's just a regular encoder, but we also use the backend mechanism to install that. So finally we're going to do a little bit on the LocalAI API, which is in fact, historically LocalAI it had no user interface. It just had a command line interface, and you'd use its functionality through the API, through the OpenAI compatible API or whatever. It in fact has its own API endpoints for certain things. And so we can use local AI through other applications which are compatible with OpenAI's API, or we can write our own integration. So we're going to do a little bit of both. We're going to use OpenCode to write a little bit of code, which I have to say, yeah, it's challenging with smaller models. Now, Ettore just added a new model, a new quantization of Quen 35 billion 3.5. So previously I wasn't able to run a model this size, but now I can run it thanks to this quantization. So we can actually write a little bit of code using open code. And I mean, this is like a very new thing. Previously I wasn't able to get these like full coding agents to work. But anyway, I digress. Let's talk about the configuration of open code. So in open code, we have to go into its configuration and describe a new provider. So we're going to put down LocalAI as that new provider, and we're going to say that it's OpenAI compatible. We're going to use the OpenAI API with it, and you can give it a name, which is LocalAI with Leadbox, which is the host we have it on. We have to set the base URL, which is just the address with /v1 on it. You have to be careful because some OpenAI clients and some applications interpret the base URL as just the domain name, and others include the v1. And yeah, it's just a minor detail where sometimes you might find that you get 404 or weird problems when you do a request, and it's actually just because this v1 is either there or it isn't there. And then we specify the models we want to use. We just have one model specified here, which is this new one, and we tell it the context size and stuff like this. Okay, so we've set that up. Now we can run open code. And it already has our model selected, but if it didn't, you could do a switch model and select it there. Okay. And then we're going to give it something simple to do, and I really have to hope it actually does it. So make a single page application in index.html that says hello world. Okay, so it should certainly be able to do this. And while it's working away, I'm going to do a curl request to make sure that Redbox 8081. Okay, so it made that HTML. That's good. Models. Okay. To do that. Okay, so then I've also done that shell request to show the model this API endpoint exists. Okay, and what kind of output it returns. So in the index HTML, I want to call the models endpoint and display each model. And change the H1 to LocalAI models. Okay. See if it manages to do this. Okay, so yep, so it's done a fetch to that address. Updated index. Okay. Let's go and get rid of that. Okay, yes, bun serve. Okay, so this I also have a script in this, a small script in this repository that it just serves the index page using bun, which I created with Claude Code because Bun's API is maybe just a little bit too niche for this model to handle, so it didn't manage to make it. Okay, and then we can go and view this web page. Localhost. Okay, so yeah, so it's calling the LocalAI API and it's displaying a list of models. And of course, you can start using like the chat endpoints to like do something more advanced, or you can use image generation, or some actual AI model stuff. But that's it for this video. This is the end, and there will be more videos following this. Possibly I'll just do the same video again in about a month's time when the UI has completely changed, all of the features have changed, because this is a very fast moving area and we're currently undergoing a lot of churn, and that's not going to change for the foreseeable future. So this video will age quite badly. Please come and back again and check, because everything will change very quickly. Goodbye.